we will have Lina Fajardo Gomez talk to us about Prodsimplicial and p-path complexes in directed graphs. So.
Great, thank you for the introduction. So my work focuses on math applied to biology. This is what this is inspired by, though the talk today will not mention biology at all. Suffice it to say that in the framework of that work in biology, it makes more sense to look at directed graphs. So everything that we do will be with directed graphs, and we're going to be especially interested in graphs that have some properties like having a unique source, unique sink. We'll look over those. I'll do an overview of what we're calling Prodsimplicial homology, then p-path homology, which are two different ways of computing homology groups and directed graphs. And then we'll just look at comparisons and when those homology groups agree and disagree. First, the property that we're interested in is what we're calling being consistently directed. So we say that a graph is consistently directed if it has a single source, a single target. So source is a vertex that has only outgoing edges. A target is this vertex that has only incoming edges. And it should have also no cycles. So it's possible for me to have a graph, say, like this, that has a cycle in the middle. But I'm not considering that. So even though this has a single source here, a single target there, that's not interested. We wanted to have single source, single target, and no cycles. Within the framework of homology, it is common to start with simplices. In this case, I am using a directed version of simplices, which happen to be consistently directed. So the usual construction of a simplex is you start with a vertex, and for each additional dimension, you add one more vertex and you make sure that all of the edges are pointing in the direction of the new vertex. We see the construction here of the first four. And the notation is that this these square brackets denote the simplex that is generated by these vertices. So whenever I want to do a simplex or a subsimplex that only uses some of these vertices, I'll just delete it or list a different set of vertices. If it is something that someone else has seen, what I'm calling here directed simplices are also called transitive tournaments in different books, except I'm not really using much more than the fact that these are complete graphs with edges between any two, such that there's a perfect border between the vertices. Now, if I were just to do simplices, I would be doing simplicial homology, except with direction. That's not very interesting. We're expanding that by using the Cartesian product of graphs, which happens to preserve this consistent orientation. That is a proposition in a manuscript, but for now, because we don't have a lot of time, I'm just going to present this result and hope that you will trust me. The Cartesian product, I'm defining it here in words, but it will maybe make more sense if I explain it in the next slide with an example. What I should have is, as a vertices, a Cartesian product of those sets of vertices of both graphs, and the edges should basically form a copy of each graph. So I should have a copy of G1 for each vertex in G2. So this is, let's say, the copy of G1 associated to X. This is the copy of G1 associated to Y. Or if I wanted to look at it the other way, I should have a copy of G2 for each vertex of G1. So here is copy associated to A, to B, to C. Now, the relationship between simplices and this Cartesian product is that simplices are prime. So it makes sense to define a product between these simplices uniquely. And that is how I'm going to define my cells. The result, the sketch is here. If you guys want to look at it, I can always come back to this slide, but I'm going to try to move quickly. I said it makes sense to define my cells for the homology. So remember, homology is going to be filling in whatever I call a cell. And then I'm going to be looking for holes in between the things that I'm filling out. In this case, I'm calling the dimension, the sum of the dimensions of the simplices that I am multiplying. And at least in 3 dimensions, it looks like polytopes or polyhedra. So we have here all the partitions of 3. I can do 2 plus 1. I can do 1 plus 1 plus 1, or I can do 3 by itself. And these are all of the corresponding products. These things are not new at all. They were mentioned by Kozlov in a book of algebraic combinatorial, algebraic combinatorial topology, some permutation of those words together, but it's the tiniest little verb that is not developed anywhere. So this is a theory we're developing now, even if it's not completely new. And we're just defining a Prodsimplicial complex, expanding the definition of a simplicial complex. The biggest difference is going to be this point over here, where instead of saying that the intersection of any 2 simplices is also a simplex, I'm going to say that the non-empty intersection of any 2 Prodsimplicial cells should also be contained in the union of elements of the collection. So slight nuance, but it's just to avoid the case where I have, let's say, 2 squares, both of which would be in 2 dimensions. The squares look like this. And I might have 2 of these together. So for example, if I add more edges like this, the intersection might be these 2 edges, but those per se don't really form the cell. However, independently, these 2 edges are in the union of elements of the collection. Now, what would it look like if I had an arbitrary graph, let's say like this one on the screen? The complex will just collect 1 dimension at a time, all of the things that match my definition. So dimension 0, easy. I just go through all of the vertices. Dimension 1, which is all of the edges, I haven't done anything groundbreaking. Dimension 2 is where it starts to get interesting. I'm going to be looking for anything that is consistently oriented. So for example, this triangle over here, this is a simplex. I can see that it has source here, target there, so it is consistently oriented. And then we also have all of these squares, which happen to be the product of 2 edges. So if I did product of 1 edge with another edge, I get the square. Those are all of those that are shaded right now. These are just darker because I should have 1 for this and then 1 for this and then overlap. It should look darker. Notice that I'm not filling this up because this is a cycle. So this is already creating a hole in my complex. If I keep going, I can find in 3 dimensions that there is a cube. This cube actually corresponds to the triple product of the edges. So I could fill that in as a solid, meaning that in, I don't know, space would not have a hole inside. It would not be just the 4 faces. It would be entirely the solid cube. And then there are no 4-dimensional cells in this diagram, so I'm not going to show any more slides here. Now that I've defined a complex and all of the things that could exist within a graph, I have to define a way to do math on them. So my structures are going to be end chains, just an extension of the usual end chain in algebraic topology. I'm just going to do linear combinations of cells. And then the simplest baby example here, I have what will eventually be a cycle. So if I go this way around the graph, I'm going to have E1 traverse in a positive direction, E2 going against the grain is going to be negative, E3 going against the grain is going to be negative. I will be interested in expressions like these. And any expression kind of like this one is going to be called a chain. I can define on chains the boundary operator, which for simplicities looks exactly like the regular boundary operator, where you simply consider the alternating sum of the simplices generated by all but one of the vertices. So whenever I use this hat notation, it means that I'm deleting the hatted vertex from the set of generating vertices. Oh, what did I click on? Okay. If I want to extend that to products of simplices, then I have to do something similar to the product rule in derivatives, where I'm doing a sum also with an alternating sum, but except it's not going to be as simple as going through each of the factors because the sum is enumerating the factors. I have to modify this slightly to more or less count the vertices. And instead of deleting the jth term of my factors, I'm going to mod out by apply the boundary operator to that term in my sum. A useful property that we have for normal simplicial homology that we also can prove for this Prodsimplicial homology is that if we apply the boundary operator twice to any cell, we get 0. And that's a desirable property. If my definition, if our definition of the boundary operator did not satisfy this property, we'd have to go back to the drawing board. So far, at least this part checks out. Now we're going to compare this to p-path homology. This is based on a paper by Grigorian and other people. So the preprints go back to 2013, but there's a more recent paper from 2020. So I'll list those at the references at the end. The definition is a little bit, let's say, convoluted. It takes a lot of steps to actually get to the space that we're going to work with. So bear with me for a minute. If I start with a directed graph, arbitrary directed graph, I can have an elementary p-path with just any sequence at all of vertices, whether or not there is an edge connecting them, just any sequence of vertices. And then we have this notation where these paths are denoted by E with a subscript sequence of vertices that we're traversing. A path complex is a non-empty collection such that if I have a path, then the subpaths that are strictly one vertex shorter will also be included in my complex. So it's akin to that being contained definition. If I give you an example, maybe it will make more sense. I can associate a path complex to a simplicial complex, which is our baseline complex for homology. I here have all of my 0 paths, which are just the vertices. I have the 1 paths, which are the regular paths, and then what is here a filled out triangle, I can associate a 2 paths 0, 1, 3. If I give these things directions, I'm not losing any information. And if I define the boundary operator on these paths, it works just as before as an alternating sum where I am removing the ith vertex from the generated path. If I apply the boundary operator, for example, to this path over here, I should do alternating sum. So if I delete the first vertex, I'll get a positive term, delete the second vertex, get a negative term, and so on. Now, I define the allowed paths to be those that are actually defined by edges on the graph. But if I try to do boundary operator on all of those, it may end up being the case that I'll want to do when I do the boundary, it may point to edges that are not actually in the graph. For example, here, if I try to do the boundary of this edge over here, or this path over here, 0, 1, 2, it will require me to have an edge 0, 2, which does not exist. For that purpose, we define slightly more narrow spaces called the spaces of boundary invariant paths denoted by omega p.
Hi there. Just so you know, you have about 2 minutes.
Perfect. Thank you. I should be rushing through the results quickly. And the important setup of this space is that while I could not really compute homology groups in the previous spaces because these allowed paths, I might fall outside of them if I do the boundary. If I stick to these boundary invariant paths, we should be good. So in their paper, they demonstrate that this boundary operator as defined on these spaces satisfies the property that we want them to be, that we want them to have. And now I can finally show you some comparisons. Some of these I just did by hand, the babiest of baby examples. Quick refresher, a homology group is defined as this quotient because I see these boundary operators as acting on linear spaces. I can define the kernel, I can define the image. And when I talk about how many holes something has, I'm going to be talking about the rank, or what we call the Betty number. For example, if I look at these 2 graphs, a triangle and a square, as Prodsimplicial 2 cells, so as Prodsimplicial cells of dimension 2, I should fill these in because they're both consistently oriented. So they should have trivial homology groups and they should be connected graphs. If I do the exact same computation longhand way with p-paths, I will get the exact same results. So this is a computation for the triangle. Here is computation for the square. And in general, in fact, because they have something similar to the Kuhnert formula, I can do this for any Prodsimplicial cell. So for simplices, it works out because they are star-like. It's not listed here, but it is a theorem in their paper. And they have a Kuhnert formula, which would show that I can continue to do these products and I will continue to get trivial homology groups. Where it falls apart is if I had something like a cone. So in this case, a pyramid would be a cone. A cone is just defined as starting with a graph, in this case, the square, and then adding one more vertex and directing everything to that new vertex. If I do that, according to the p-path homology, this will be filled in, so this would have trivial homology groups. But in the Prodsimplicial case, I would have solid faces on the outside, but it would be hollow inside, so it would have a non-trivial H2. Conclusions. Cones are not the only counterexample. We do also have some suspensions, which are kind of like double cones that would have two vertices that I'm drawing everything towards, starting from any graph. Or if I had something like a loop, so a cycle like this would also result in different homology groups. And there might be other families of graphs where these disagree. So we would like to see if there's a way to characterize them in future work. This work is done not by me, but by a group of people in a research group that is funded by Southeast Center for Mathematics and Biology and the Simons Grant. Thank you. A little bit rushed, but here are the references if anyone wants them. And if you guys have any questions.
All right, let's have a round of applause for our speaker. I want to put a reaction. Yes, any questions?
I have a question.
Mm-hmm.
So I guess I don't know very much about like math biology, but I'm curious about if you could say a little bit more about like your motivations and how this connects to that.
Yeah. So let me see if I can add a new page over here and I'll just make a quick picture. All right. So what we're studying is DNA rearrangement. So suppose that I have something like a DNA strand, and on this DNA strand, actually, no, let's do 2 DNA strands, because the goal is going to be that on one DNA strand, I have pieces of a gene that may be out of order. So if I put labels on this to say this might be the first piece, but then this might be the second piece, this might be the third piece, fourth piece, fifth piece, these have names, doesn't matter. And when I'm done rearranging them and moving them around, they should all be contiguous. So this is a fully functional gene. I can read this and actually produce a protein. Here it's, let's say, stored somewhere, like saved in a computer and let's see, encrypted somehow. So what we're dealing with there are what we call pointers, repeat sequences here and here that tell me where to join. So I might call this 1, 2, and then this is going to glue with segment 2. So I'll label this 2, 3. Wherever these repeat, I know that it's going to join. This produces a sequence of what we're calling double occurrence words. And there are reduction mechanisms on these double occurrence words. Like you can look for patterns that either repeat or return. So you can have words of this form. They might be U, Y, U, Z, where we either have this word repeat, or maybe you'll have a word and then it's reverse. Any pattern kind of like this one gets deleted. Based on those, we create a graph. And on those graphs, we're studying all of the paths where we reduce the word to the empty word. Sorry, it's kind of convoluted to explain how to get to this point, which is why I didn't make it into the 15-minute version of the talk. But that's what we're looking at. These words describe the scrambling of the DNA before it gets put into functional form where I can make a protein. And the homology groups should tell me something about the type of scrambling. Like I could compare the scrambling between two different genes by comparing the graph that comes from the corresponding double occurrence words.
Great.
Awesome, thank you.
So I think we should move on to our, I'm sorry to cut you off.
No,
but
you're good.
we should move on to our next one.